NASA's Lucy mission is going to be the first mission to explore the Trojan asteroids. These are asteroids that live in two swarms, one that's ahead of Jupiter and another that's behind Jupiter. And we want to go and look at these building blocks of the planets, the ones that didn't get accumulated into the planets, to really learn about the evolution of our solar system.
Lagrange points are these stable regions of space. They're around pretty much every planet in the solar system. Jupiter, by virtue of being the largest planet in the solar system, it also has the biggest Lagrange points. And these are little stable reservoirs where asteroids get in, but they never come out. In reality, what we have is sort of a snapshot of what the solar system looked like billions of years ago.
Early in the solar system, the giant planets were migrating outward, away from the sun. And at one point, there was chaos in the solar system. Some small bodies were ejected out of the solar system. Others could have been trapped in these Lagrange points. And that's one theory for how the Trojan asteroids came to be where they are today.
My job as a mission architect here at Lockheed Martin, it's very interesting, and it sort of encompasses the biggest picture of the mission. What is the trajectory? What sort of propulsion do you need to fly that trajectory? What does the spacecraft look like? So in the case of, for example, Lucy, it's like, okay, it's going out 5 times further from the sun than the Earth is. And so it's going to need big, huge solar arrays just because of that.
Lucy has 3 scientific instruments on board the spacecraft, and we'll also be using 2 of the spacecraft's subsystems to contribute to the science investigation. With the LORRI instrument, we'll be able to get panchromatic images, which will tell us about the geology, and the crater history, which gives us the age of the surface. With the TESS instrument, we'll be able to measure the temperature of the surface at different points, and with the RALPH instrument, we'll be able to measure the composition of the surfaces. The Jupiter Trojans, they have a variety of surface characteristics. They have different colors and different surface compositions, and that leads us to believe that maybe they formed somewhere else. In choosing the Lucy targets, we wanted to be able to compare different objects that have different surface properties, but a very similar orbit. Lucy will visit 1 main belt asteroid and 7 Trojan asteroids.
I don't think there's been a single NASA mission that will have visited as many objects on separate orbits in the solar system as the Lucy mission will. We launch in October of 2021. That trajectory just basically does a 1-year loop around the sun and comes back to Earth in October of 2022. And that will slingshot us out now onto a trajectory that takes a little more than 2 years to come back to the Earth. Now we're moving a whole lot faster than we were. We get that trajectory set up, and that second Earth gravity assist takes that velocity and redirects it in the direction we want. That'll take us out to the Trojan space.
On our way out to the L4 swarm of the Trojans, we're going to visit a main belt asteroid. That main belt asteroid is named Donald Johanson, after the discoverer of the Lucy fossil. We named the Lucy mission in honor of the Lucy fossil because we learned so much about hominid development and evolution from that fossil, just like we're going to learn about the solar system evolution from the Lucy mission.
From there, we take a couple years off and we continue to cruise up until we get to August 2027. And there we encounter our first Trojan asteroid. It's called Eurybates. It's the product of a huge collision that happened millions and millions of years ago. Something big hit it and just blew it apart. And so Eurybates is the biggest chunk of that cataclysmic impact. And it's a C-class asteroid, which is kind of interesting because there's a lot of C-class asteroids in the main belt. There's very few of them in Trojan space. So that's one of the mysteries we're going to get at is, okay, why is Eurybates so different? As we've studied it and tried to refine its orbit, we've discovered it's got a little moon. And so we're going to try to get pictures of that too as we fly by. And about a month later, in September of 2027, we're encountering our second Trojan asteroid, Ptolemy. So it's one of the smaller objects. We're flying by at about 6-7 kilometers per second. We have to take pictures like crazy as we fly by, but we're not stopping at any of these. We come to our next object, Lucas. It's wash, rinse, repeat. And so we snap pictures like crazy at Lucas. And then about 7 months after that, we do the exact same thing at another object called Oris. And that's the last L4 swarm object that we're going to be visiting. And from there, we start dropping down back into the inner solar system now. So we were out past Jupiter's orbit a little ways. Now we're falling back in towards the Earth. So the trajectory is sort of set up to sort of return back to Earth for free. And we use that to redirect the trajectory now towards our final Trojan asteroid. And so this is an object out in the L5 swarm. So it's trailing Jupiter by about 60 degrees. It's a roughly equal mass binary system called Patroclus and Menecius. You can imagine it's sort of like this dumbbell in space. So imagine a great big dumbbell spinning around, but there's no bar there. It's just the objects orbiting each other. It's a very rare thing to find in the inner solar system. However, if you look out past the orbit of Pluto, equal mass binaries are kind of common out there. Another clue is like, okay, are these objects in the Trojan swarm, are they maybe related to the Kuiper Belt objects out there past Jupiter? And if they are, this will be amazing. We can go and visit Kuiper Belt objects by just going out to Jupiter.
We really have never seen Trojan asteroids up close before, and we want to understand their geology, look at the craters on the surface to understand the history of their surfaces, understand the composition of their surfaces so that we can maybe learn something about where they formed. And all of those will be clues to help us understand how the solar system evolved.